Good morning. Good morning. I am Dr.S.V.Mahesh Kumar, Associate Professor, Department of ECE, Bharat Institute of Higher Education and Research. In the earlier presentations, we discussed about how to design a embedded system using a microcontroller, how a partitioning is happening in a microcontroller and a embedded system design, what are the elements are considered and how the microcontrollers are chosen for a embedded system design and what is how the memory is allocated and partition is done for program memory and data memory with respect to applications, and as well as what are the hardware and software design flow used. Everything we discussed in the past two presentations. In this presentation, we are going to discuss about for functionalities for system design. Mainly we are focused on timers and watchdog timers, which are related with the functionalities for a real-time system design. These are the contents of my presentation. We start the session with what is timer. After that, we discussed about what is the need for a timer and how the timer is differentiated from the counter and what are the types of timers used in real-time embedded systems and what is the role of a watchdog timer and watchdog timer signals, what are the signals are related with a real-time operation of a watchdog timer, and then what are the registers are related with a watchdog timer and its operations, and then how to enable and turn off the watchdog timer, and finally we conclude the session with a real-time examples. This is the reference used for this presentation. Okay. The first one, timer. What is a timer? A timer is a specialized type of clock which is used to measure time intervals. A fixed time interval is fixed. For example, a time interval is 10 means we need to fix the value 10. After that, the timer is used to measure that particular time interval by a countdown process. So it is a device that counts down from a specified time interval and used to generate a time delay. The practical application of a timer is it used to generate a time delay, a fixed time delay. We need to fix the delay time according to the real environment scenario. So the timer is working according with this. What are the parameters? What are the things we need to concentrate at while fixing a specific time interval means the timer value, the count value, time value is not always closer to your real environment time, which is measured in seconds or something. So suppose I'm setting the 10 value means 10, 9, 8. It not doesn't mean that it is a 10 second, 9 second, 8 second. It is a value. So you need to correlate the value and the time required to take these values, count on these values from 10 to 9, 9 to 8, 8 to 7. What is the time required to count on from 10 to 9? And we need to correlate what is the real time and as well as the value. And then what are the real time is depending upon this 1 second, 2 seconds, 3 seconds time delay means we need to first set what is the crystal oscillator used and then what is the frequency of operation, and then we can easily calculate the time from the frequency operation. F is equal to 1 by t. Then we can easily find out the real time with respect to the count value. So we need to correlate the count value as well as a real time. So these are the elements of a timer, on-chip timer with a microcontroller. It's an on-chip timer in a microcontroller. You can see what are the elements. So it communicated through the microprocessor or microcontroller with a data bus. After that, a write signal is there, and then entire operation is synchronized with the help of a clock signal, and then output is there. This is the timer output. It is working according to the clock signal input and then oscillator frequency. Why we are using timers? What is the need for a timer? The timers will play an important role as it is the heart of the embedded system, because a real-time embedded system handles a real environment issues which requires a time delays and other time related functions. So we need to use this timers and it is the heart of the embedded system. What is the example? The example for a timer control the blinking rate of the LED or to generate delay on the source code. We suppose you want to activate a LED for a particular seconds means, for example, your LED will be on in 5 seconds. After that, it should be off for a 5 second. Again, it is on and a 5 second. Again, it is off for a 5 seconds means the operation, the entire operation is uses a timer and the time delay is generated by the timer. The 5-second time delay is generated by the timer. To generate this 5-second time delay, we need to fix a count value which is closely related to the oscillator frequency as well as a real time. This is a difference between a timer and counter. We need to differentiate the timer from the counter. So first, a timer is incremented for every machine cycle. Compared with timer, the counter register is incremented considering 1 to 0 transition at its corresponding to an external input pin. And then for a timer, the maximum count rate is 1 by 12th of a oscillator frequency. So suppose I am using a 12 megahertz means the value is 1. Suppose I am using 24 means the value is 22, like that. Here in a counter, a maximum count rate is 1 by 24 of the oscillator frequency. So suppose I am using 24 megahertz means the count value is 1. Suppose I am using 48 means the value is 2, like that. A timer uses the frequency of an internal clock and it generates the delay. So the delay signal is, and suppose I want to generate a 5-second delay or 10-second delay, is closely related with the frequency of internal clock. This is the way how the timer knows how it is a 5 seconds. It is based on the frequency of internal clock only. In a counter uses an external signal to count pulses. So it receives external signals and count what is the on period and off period from the external pulses. In this way, the counter is different from a timer. So next, the different types of timers used in embedded systems. Embedded system is a real environmental system. So we need to use a different timers according to the applications. Each timer has its own advantages and disadvantages. Let us discuss one by one. The first one is the mostly used one, that is Watchdog Timer. The Watchdog Timer is mostly used in many real-time systems. So Watchdog Timer, if the system detects any malfunctions or errors while in its normal operation, this timer immediately works on solving the issue. So it is used to solve a real environment problems and then immediately it responds according to the errors. So when the error signal is detected, it is activated immediately according to this error signal and it goes for a reset position or any other things necessary. Moreover, when the software not operated properly or hangs out of the blue, this timer uses the 16-bit counter to reset the system. Reset is the immediate reaction of a Watchdog timer if a software issues are occurred. Even a software hanging, everything is occurs, then also the timer, Watchdog timer will react and it will reset the micro system. What are the features of this Watchdog timer is, Watchdog timer can detect program errors, code crashes, the software hanging, and even power variations also. So it works according to all these issues. It will immediately react and then it will reset the system. So uses the embedded reset signal present in the CPU to reset the OS. How to reset the OS? The Watchdog timer uses the reset signal of the CPU and make the activity of the program in its normal form. So the program will become its default condition and it will error free. Now it is error free. So next timer is general purpose timer. These are the basic timers used for various purposes such as starting a device or measuring the time duration. You need to measure a time duration of a particular signal. Then this is the appropriate timer used for that. What are the features of this general purpose timer is to provide a periodic intervals are needed. Example is blinking of an LED. LED is blinking for a particular second. After that, it is off and then again on, off like that. The period between one on state and off state is a fixed one. So it is a periodic intervals. So you need to generate a periodic intervals. So for this purpose, we can use this general purpose timers. And then the next feature is to measure the length or duration between two scenarios. Example, the time to press two keys. So the time between two on status can be measured with the help of a general purpose timers. The next one is interval timer. The interval timer provides an output signal when it starts and ends in a programmable count. The output signal might cause an interrupt to occur. What are the features of this is, it can be a one shot or a periodic timer. The similar in the previous case we discussed about what is the periodic operation. So it can be one shot or periodic timer. In one shot timer, it will signal for a single time and then it will stop its counting process. So the signal is controlled and it was signal for a single time only and then it will stop and its counting process will be stopped after that single time signal. For periodic one, the timer signals for some amount of time until it reaches a specified value. So you need to fix a value for that and then until it reaches the value means the counter process when it reaches the zero up to reaches the zero value, the timer will operate it. So this is known as a interval timer. It will be operated for a particular interval, time intervals. So this is the functions and features of this interval timer. The next one, a Systick timer, used for operating in a single mode operations. It is used for a single mode operations and it is periodic as well as decrementing. The count value decremented from 10, 9, 8 like that. Any decrementing value is the process. And then they are used in real-time operating systems to generate periodic interrupts. So interrupt is the signal which stops the processor's current operations. So interrupts are the external signals which stops the processor's current operation and it will lead to other operations. So these type of timers are used for real-time systems to generate a periodic interrupts. What are the features of this timer is it provides a time delays. So whenever the time delays is required, it is definitely useful for a real environment system. For example, we can use the motors in our robotics applications. Many robotics applications we can use the motors. First, so the motors are running in the forward direction. Suppose I want the vehicle is moving in the reverse direction means we need to rotate it in anti-clockwise direction by switching the powers. The time duration between this forward and reverse motion can be decided based on the time delays generated by the timers. And it can, what is the other feature of this timer is it can generate a periodic events smoothly. This is the major advantages of this timer. And the next one is a real-time clock. We heard about this word, real-time clock. It is low resolution in comparison to a general purpose and other timers. So it's a low resolution device. What are the features? Why we go for this real-time clock? These are mainly used to generate time in a readable format. So we can know what is the time delay from a display itself. So it generates the time in a readable format is the major feature of this real-time clock. And then it have a rapid resolution in 1 second. The resolution is also a rapid one for a second period also. And then functions as a digital watch and used to tell the time to the user. In a microprocessor, and microcontroller users, the designers as well as users can know about what is the time period, what is the time delay, everything you can know. So that is the reason it is called as a real-time clock. A coin cell is used to power up. It is powered by a coin cell itself, a CMOS battery is like that, so that it can still run even the system is turned off. It is a very, very important feature of a real-time clock. It's like our system clock. It won't be stopped when you stop the system. It is still in running. After that, we are enabling, we are switch on the system. We can see the updated time only, not the stopping time. If the battery power is failed, you can see the earliest time. This is the best example. So whenever you switch off the system, the clock won't switch off. It is still run and it is still show the timing, real-time timing. That is the reason it is known as a real-time clock. So let us discuss about the Watchdog Timer. You can see the Watchdog Timer in this diagram. It's a piece of hardware that can be used to automatically detect software issues. So you need to detect, because it is difficult to monitor a software issues continuously. So you are using this Watchdog timer. So this hardware is automatically detect the software issues and it reset the microprocessor. This is the major role. So whenever the software issues occurs, you need to reset the microprocessor. For that purpose, you need to use one device. That device is a Watchdog timer. You can see here, the Watchdog timer is in the left side and the processor is in the right side. You need to reset the processor whenever software issues are occurred. So a Watchdog timer communicated to the processor through the reset. Then how the processor communicated to the Watchdog timer, it sent a restart signal to the Watchdog timer. If the Watchdog timer received a restart signal, then it reset the processor. What is the meaning for that reset signal is the software issues or other issues acquired. So we need to reset the microprocessor or controller at this time. So that is the role of a Watchdog timer. How the synchronization between the Watchdog timer and processor is acquired means you be using a clock signal. So clock signal is used to synchronize the operation of a processor as well as a Watchdog timer. So this is the role of a clock signal. These are the various Watchdog timer signals. So supply is there. The reset is the active low signal. So whenever the issues are acquired, you need to reset your microprocessor or the embedded system connected to your Watchdog timer. So this is the Watchdog timeout signal for a one clock cycle. This is a Watchdog time period, you can see. And this is the reset timeout. You can see here the switchings. It's a reset timeout. And then this internal reset is also there during this period. The Watchdog timeout to this period. So the internal reset signal is enabled. You can see here the Watchdog timeout to, and then this one, the internal reset is enabled. This is the setup of a Watchdog timer. Watchdog prescaler is there. The prescaler is controlled by a 128 kHz oscillator. We already discussed about the relationship between the oscillator frequency as well as a time or count process. So this is the used 1/12th and 1/24th. We already discussed in the previous slides. So this is used. So oscillator is an important key factor phenomenon. So the entire time parameters are decided with the help of this oscillator only. So this is a Watchdog reset signal, and then various prescaler signals are there, and then various enabled and interrupt enabled signals also there. So moreover, this is the microcontroller unit reset signal is also there. So the timers and its prescaling process, and then signals related with the Watchdog timer, and then interrupt generated and the reset generated are shown in this figure. The watchdog timer is essentially a counter that increments based on the clock cycles of an on-chip 128 kilohertz oscillator. What we already discussed. What's the role of a 128 kilohertz oscillator? It increments based on the clock cycles. That is the role. The watchdog timer forces an interrupt or a system reset signal when the counter reaches a given timeout value. In normal operation, the application code needs to issue a watchdog timer reset signal to restart the counter before the timeout value is reached. So the timeout value is the key phenomenon for reset. If the system does not restart the counter, an interrupt system reset will be issued. So this is purely depending upon the system signal. If the system does not restart the counter, an interrupt system reset will be issued. Through the interrupt, it will be restarted. This is the key phenomenon. Watchdog timer modes. It is operated in various modes. So 3 operating modes are there. The first one, through the interrupt mode, system reset, interrupt and system reset. Then what are the functions or acquires during this 3 operating modes we will discuss one by one. So the first one, the interrupt mode. The watchdog timer forces an interrupt when the timer expires. So this is a major point of this interrupt mode. It forces an interrupt when the timer expires. The timer reaches the value, then it forces an interrupt signal. So that is the reason it is called as an interrupt mode. This interrupt can be used to wake the device from any of the sleep modes and also as general system timer. This is enabled by setting the interrupt mode bit. So in the watchdog timer control register. So this interrupt mode is enabled with the help of an interrupt mode bit available at the watchdog timer control register. Then system reset. This is the next mode of operation for a watchdog timer. In system reset mode, the watchdog timer forces a reset when the timer expires. So it is operation is controlled by, in the previous case, it is controlled by the interrupt. Here it is controlled by the reset signal. So this is the reason it is called as system reset. In the system reset mode, the watchdog timer forces a reset when the timer value expires its limits. This is typically used to prevent system hang up in the case of runway code. Or running a code and the limit is there, the timer value is not expressed this, then we need to use the system reset mode and then we will reset the timer values. This is enabled by setting the system reset mode bit and then in the watchdog timer control register. The previous case it is enabled by an interrupt bit. Here it is enabled by a system reset mode bit in the watchdog timer control register. So in both cases, we are using a watchdog timer control registers. We are enabling the bits, different bits like interrupt bit or reset mode bit in the watchdog timer register. And the third mode of operation is interrupt and system reset mode. Interrupt and system reset mode combines the other 2 modes by forcing an interrupt and then switching to the system reset mode. So forcing an interrupt and switching to the system reset modes. This mode will offer a safe shutdown by allowing time to save critical parameters before system reset. So it offers a safest shutdown. Okay, by allowing time to save critical parameters before a system reset, all values are saved in the memory before system shutdown. So this is known as a safest shutdown operation. This is enabled when both the interrupt bits are set. Interrupt enabled bits are set, so it is purely dependent upon interrupt enabled bits. So this is the watchdog timer timeout period. What is we discussed about timeout period and what is the watchdog timer timeout period. The watchdog timer prescale bits of the watchdog timer control register determine the delay in the watchdog timer. So what is the delay? What is the timeout period of a watchdog timer is decided based on the prescale bits. So these 4 Prescale bits are there. Watchdog timer, prescale bit 3, 2, 1 and 0. And these are the number of watchdog timer oscillator cycles related with this prescale bits conditions. And then this is the oscillator time. So first, all bits, all prescale bits are 0. Then this is a 2k number of oscillator cycles. So 2 into 1024. So this is 2048 oscillator cycles. So oscillator time period, corresponding time period is 16 milliseconds. Similarly, we are enabling the first one, and this is a 4K, so 4 into 1024, 4096, and the time period is 32 millisecond time. And then 8K means we are enabling this 8 into 1024, 8192, and then next we are enabling 0 and 1, and this is 16K, and we can see here this is 0.125 seconds, and then the enabling this one, and then this is 32K, and then this one 64K, 0.5 seconds, and 128K, 128 into 1024, this is 1 second, 256K by enabling the 3, and then 512K, and then 1024K, so it is increases up to 8 seconds. So this timing is related with this watchdog timer prescale bits. We can easily remind this 0, 1, 2, 3, 4, like that. So 5, this is 8421 coding. So 8421. So this is 0, this is 1, this is 2, 2 plus 1, 3, and the next one is the fourth one, and then 4 plus 1, 5, and then 4, 2, 6, 4, 2, 1, 7, and then 8, like that. They can use this. And again, the value reaches 1. So this is the conditions. So every operations, the timeout period is controlled by enabling various prescale bits in the watchdog timer. So the prescale bits are enabled according to this time period. So watchdog timer system reset flag. So watchdog timer system reset flag in the microcontroller MCU status register is set if a watchdog system reset occurs. So you need to set and reset this flag according to a system reset condition. So it is set if a watchdog system reset occurs. So otherwise it is reset or it is 0. If it is set means the value is 1. The watchdog timer register flag is cleared by power on reset or by writing 0 to it. So 1 means it is set, 0 means it is reset. So it is reset according to a power on reset. To identify the reset condition, the user should read and then reset the watchdog timer reset flag as early as possible in the program. So everything is controlled by the user. So you need to identify whether the condition is a reset. If it is a reset condition means read the reset signal, and then accordingly you need to set the flag register status according to the reset signal. If the register is cleared before another reset occurs, the source of the reset can be found by examining the reset flag. So you need to concentrate about this flag, whether it is highlighted by a yellow color. If it is set means 1, if it is 0 means it is reset. So we need to always look for this watchdog timer system reset flag to know about the condition of a reset. How to turning off a watchdog timer? So we need to use a watchdog timer for find out real environment software issues and other issues, and reset the system when the issues are occur. So that is a major role of a watchdog timer. How to handle this watchdog timer we'll discuss. So to prevent unintentional disabling of the watchdog, a special turn off sequence must be followed. Otherwise, we don't know whether the watchdog timer is disabled. We don't know about that. So you need to prevent the unintentional disabling of the watchdog. So we follow a certain procedure to turning off the watchdog timer. Well, the main reason is to avoid a unintentional disabling. In the same operation, a write logic to a watchdog timer enable the bits. So you need to use a write logic 1 to enable the bits. Enable means 1, disable means 0. So we need to enable it by a logic 1 bit. So a logic 1 must be returned to a watchdog timer enabled even though it is set to 1 before the disable operation starts. So we need to enable it, then only we can know that what is the condition of a watchdog timer. Within the next 4 clock cycles, write a logic 0 to watchdog timer. This disables the watchdog timer. So this is the process. First, we need to enable it by a logic state 1, and we need to disable it by a logic state 0. We are following this procedure to prevent an unintentional disabling of a watchdog timer. So logic 1 and logic 0 are used to enabling and disabling a watchdog timer. So this is the practical programming example of turning off a watchdog timer. You can see this is the turning off functions highlighted by green color. You need to reset a watchdog timer. So after that, a logical 1, we already discussed about that. We need to write a logical 1 and then the 0. So first enabling a logical 1 here. After that, next 4 cycles we are using 0. This is turn off the watchdog timer. So this is the simple process of used for turning off a watchdog timer. These are the multi-thread examples for a watchdog timer. So these are the 3 processes: read sensor, control motor, and the display the status are there. In this 3 different processes are there, the sequential processes are there. So we need to handle the timers according to this. So we are using the process a sleep. Here the sleep period is 40. Compared with the first operation, the second operation is 80, and the third one it is 95. So we need to use a different sleep periods for this to handle a multi-thread. This should be a different 40. The second one is greater than the 40, and the third one is greater than the second one, like that. So we are following for a multi-thread application. So a practical examples. How it is used, in what limit the watchdog timers are used. This is the practical example it is faced during a Morse Pathfinder project. So priority inversion occurred on the Morse Pathfinder project. It's a mission, it's the greatest mission, Morse mission. Everyone know about this. So what's the role of this watchdog timer during this Morse project? A huge Morse project is, it faced a problem. A high priority communication task was forced to wait on a mutex held by a low priority task. So your low priority task overcome a high priority task. So surely it is an issue. So you need to reset. So system reset is issued by its watchdog timer. It's also a part of the system. So it issued a reset signal and brought the system back to its normal operation condition. So in this kind of situation, it is difficult. You need to reset the system according to a real environment problem detection. So this is a great example for a watchdog timer, which is used in Morse Pathfinder mission, which reset and back the system in its original position after a low priority task is overcome, forced to wait a high priority communication. So system reset is acquired by a watchdog timer. This is the example, one of the example for your watchdog timer. Okay, let us conclude the system, the session with this point. Thank you.